Hello, welcome back to Engineering 211 Statics, and I wanted to pick up where we left off last time, in that we had started talking about drawing Freebody diagrams and using equilibrium equations. So if I pick up on that equilibrium equations and look at the equations that we have the sum of the forces is equal to 0. That was looking at a system that does not accelerate, and using Newton's second law, setting the acceleration equal to 0, we get the sum of the forces is equal to 0. And we could then expand this and look at the typical coordinate system. The sum of the forces in the x is equal to 0. The sum of the forces in the y is equal to 0. And the sum of the forces in the z direction is equal to 0. And then if we look at the moment, I think I talked about this last time, if we have no rotational acceleration, we would have the sum of the moment is equal to 0, and this then expanded allows us to talk about the sum of the moments about the x-axis is equal to 0, and the sum of the moments about the y-axis is equal to 0, and the sum of the moments about the z-axis is equal to 0. So for a full 3D system, we have 6 equations, so with 6 equations we could tolerate then 6 unknowns and hopefully solve for the 6 unknowns. Now occasionally we'll venture into this, later we'll venture into this, but for now let's look at the 2D case, where we'll have some of the forces in the x, some of the forces in the y, and then if you look at a right-hand coordinate system, so take my x and my y, the right-hand coordinate system, right-hand system is going to give z like that. So if I'm doing some of the force in the x, some of the force in the y, I'd look at the rotation around the z-axis, or tendency to rotate around the z-axis. So I would have some of the forces in the x is equal to 0, some of the forces in the y is equal to 0, and some of the moments, we'll normally just say some of the moments, but if we were to be very specific, we could say some of the moments about the z is equal to 0. So this then gives 3 equations, and we could solve for 3 unknowns. Okay, 3 equations and 3 unknowns. And this is, we'll be doing quite a bit of work with this before we move into the full 3D case. Some other cases that I'd like to look at that are probably worth considering would be, what if we talk about a collinear case? With a collinear case, we might have all of our forces on a line. So we might talk about this F1 and F2, and then maybe F3, and all of those would be on a line. So if I look at the equations that I would have to use, if I say that my x direction is here and my y direction is there, some of the forces in the y gives me 0 equals 0, or a trivial equation. All of the moments are coincident on a line, so I don't have a moment. So some of the moments about z would give me an equation 0 equals 0, a trivial equation. So I really have only one equation. The sum of the forces in the x direction is equal to 0. And then that means I could really only tolerate one unknown. If I were to solve this problem, for instance, F1 and F2 would have to be known if I was to find F3. Well, another case that we talk about is concurrent at a point. So concurrent at a point, let's say that we have a body here, and all of the forces are concurrent at a particular point. We could say F1 and F2 and F3. Now if we look at the equations we have there, again the moment equation, there's going to be no moment produced. They're all concurrent at a point, so that would be a trivial equation 0 equals 0, and whatever coordinate system we have, x and y, let's say, we would really only have some of the forces in the x is equal to 0 and some of the forces in the y is equal to 0. So we could only really tolerate 2 unknowns. One of these would have to be known if we were to find the other 2. And this, in fact, if you're going through your reading and trying to figure out, well, what's the difference between Chapter 3 and Chapter 5, why are we skipping around, this is Chapter 3. Okay, it comes before the moment. We went ahead and we studied and talked about moments, so we can do 3 and 5 simultaneously. But Chapter 3 does not deal with moments because they are all concurrent at a point. There is no moment produced. Well, we could continue on if we wanted to and talk about another case, which would be parallel. This would be page 2. So if we look at a situation where they're parallel, so we've got a variety of forces here, F1, F2, F3, and these are at right angles. We know those are parallel, and we could talk then, if I look in the y direction, again, I get some of the force in the y direction, I get a trivial equation, 0 is equal to 0. So really I'm only left with some of the force in the x is equal to 0 and some of the moments is equal to 0. So again, I have a situation where I only can tolerate two unknowns. Well, from this we could look at a general case. A general case might be we have this body and we have a variety of forces. They're not concurrent at a point. We could even apply moments to it. F1, F2, F3. Maybe we have a moment here like that. And with a XY coordinate system, I could say some of the forces in the x direction is equal to 0, some of the forces in the y direction is equal to 0, and some of the moments is equal to 0. So with that, I have the 3 equations, and I can then hopefully solve for 3 unknowns. And in fact, these 2 are Chapter 5, if we're keeping track of the reading. Okay, so those are some cases that will come up. A couple other things that sometimes come up is whether something is over-constrained or under-constrained. So let's say that we have something like this, maybe under its own weight, some sort of a block or package or something like that. If I were to support it with a force here, and a force here, and maybe if we're concerned about moving side to side, I could say that I have a force there, so I have R1 and R2 and R3. I could say that this is properly fixed. That differs from a situation where I might have something like this. R1 and R2, these are reactions. R3, where I would have, I had maybe it acting under its own weight here. This acting under its own weight, that would not be fixed. You could imagine these forces would have to take on an infinite value to support this load because of their orientation, presumably at right angles to that load. So this is not fixed. And the last case is probably the most important case that we'd be able to recognize, is let's say that we took something like this first one, and if a little is good, a lot is better, so maybe we'll add something like this, R1, R2, R3, and R4, putting so-called belts and suspenders on the thing. We've got it constrained like that. But remember, if the weight is the only thing that is maybe known here, we would have an unknown in R1 and R2 and R3, which was not a problem over here because we have 3 equations, 3 unknowns we can deal with. But here we add this fourth, we have then a 4th unknown and we have a problem. So unless we can make some assumptions and try and neglect one of these, say it's very small in comparison to the others or something like that, we are forced into a situation where we have only 3 equations and we have 4 unknowns, and we will call this a statically indeterminate situation. Statically indeterminate. That's kind of long, almost ran off the page there. A lot of times we'll just say statically indeterminate. And at this point, like I said, we could sometimes maybe say that, well, one of these is going to go away because of some situation, if you're supporting it with a cable and the cable won't take compression or something like that. Sometimes we can get this back to something that looks like this, but oftentimes, most of the time, we have to just throw our hands up and say, well, we can't do this. Now, spring term, when we start looking at things as non-rigid, that they can deform, we'll have a deformation equation, another equation, and we'll have that extra equation we need to solve the problem. So when someone talks about something being statically indeterminate, that's what they're talking about. And at this point, we really end up just kind of throwing our hands up and not being able to go forward from there. Well, what I'd like to look at next is put our technique of drawing the free body diagram and using these equilibrium equations to practice with a problem. So let's say we're given this, and let's say we're hoisting a load. We'll have a pulley arrangement here. Okay, so we've got that. We'll say that this is C, this is B, this is A, and I guess we need to support this point right there. And we'll say that we got a 1,000 pounds there. So we're given that, and we'd like to find the tension T up there and the forces at the bearing at C. Okay, so we'd like to find this tension up here. We're pulling on this thing. Almost got off the paper here, but we've got some tension T up there that we're pulling on that with. That's at 30 degrees with respect to the horizontal. And we'd also like to find what we have in terms of the bearing reactions at C. If we're going to design this bearing or that pin there, we'd like to find those reactions. So lots going on at C. Maybe we'll draw a free body diagram at C. So that would seem reasonable. Free body diagram at C. Let's see what that looks like. And really, from any problem that we do going forward, we'll probably draw free body diagrams. We should always draw free body diagrams. So I'm going to say that I have something like this. We've got this tension force T, and that's at 30 degrees there. And then this C, this would be a pin. We'd drill through that and we would put a pin. So I'm just going to go ahead and take CX like this, and then we could say that we have CY like that. Okay, CY being the vertical. I'll take for the entire problem, I will take X positive to the right, I'll take Y positive up. The other thing, I should probably put this tension here. Why don't I call this T2? Now, T2 is an unknown, CX is an unknown, CY is an unknown, and T is an unknown. So the problem here, I have 4 unknowns. So I might be tempted to throw my hands up, say it's statically indeterminate, but before we do that, why don't we go draw a free body diagram of something else? So maybe I'll say that I have a free body diagram of B. So I'm going to separate this B out and look at that. So let's do that. So the free body diagram at B is going to look something like this. Where I would have this force here, which would be the same, equal and opposite by Newton's third law as that. So if this was T2, this would have to be T2. Maybe I'll say that this is T3, and we'll say this is T4. Now we have a case here where all of these forces are parallel, right? So I only have two equations. I have some of the forces in the y direction or the vertical, and I have some of the moments, but I have three unknowns, T2, T3, and T4. So again, before we throw our hands up, let's try one more thing. Let's try the free body diagram at A. So the free body diagram at A, I'm essentially going to look at this thing. I mean, you could do a quick free body diagram for the load if you wanted to. Most people are pretty comfortable with this. If you have this 1,000 pounds acting down like that, you would have some required force acting up, which would be 1,000 pounds, right? So when I draw this free body diagram at A, it's going to look like this. We're going to have this 1,000 pounds acting down from there, and then I've got these two forces going up here. This one here would be the same as this, so this is going to be T4. And then over here we've got this one, which we'll say T5. Hopefully we don't have to deal with that. So if I go through this then, I've got, again, a parallel situation, so I only have two equations. The sum of the forces in the vertical or the y direction, sum of moments. My sum of the forces in the x gives me a trivial equation, 0 equals 0. If we wanted to see that, if this is, we'll stick with x and y like that on all of these. If I sum the forces in the x direction, setting that equal to 0, I get 0. 0 equals 0. Trivial equation. That doesn't help me very much. If I sum the forces in the y direction, in the vertical direction, I'll go ahead and take up as positive, setting that equal to 0. And we could assume down as positive. You'll see here that I would have T5 plus T4 minus 1,000, which hopefully makes sense. This plus this has to support that 1,000, doesn't it? Well, I need to figure out T5 and T4. So what I will do is I'll do the sum of the moments about the center on this thing, setting that equal to 0. So I'm going to sum the moments about there. We will assume that the radius on this thing is r. That would be the same either side because it's round. So I could say that I have, taking clockwise as positive, T5 times r minus T4 times r, because this one's going to tend to rotate it clockwise. This is going to rotate it counterclockwise. Well, if I go to solve this equation here, I can say then that T4 is equal to T5. If you recognize that T4 is equal to T5, you could say that T4 is equal to T5, which they would then have to be 500 pounds, wouldn't they? They have to be 500 pounds because they need to satisfy that equation. So now we have the little piece that we needed here. We can go back to this one. This becomes then 500, doesn't it? We substitute that back in, and we could do the same thing here. Sum of the forces in the vertical direction or the y direction is equal to 0. What do we come up with? 0 is equal to T2 plus T3 minus 500, right? Or that T2 plus T3 is equal to 500. Now, do we know T2 is equal to T3? Yeah, if we did a moment equation about here, recognizing that that distance is the same, I'm not going to belabor that point, but if you did some of the moment about this point here, you get that T2 is equal to T3. So we could then conclude that T2 is equal to T3 is equal to what? 250 pounds, isn't it? So now I take this T2 that I just found is 250, and I can put that up here. 250 pounds. I substituted that back up there. So now what I could do is maybe I'll come up here and sum the moments. I'll sum the moment about the center line here, setting that equal to 0. What do I get? Well, this is operating at some distance, the radius. So I'm going to have r times t if I'm taking clockwise as positive, and you take counterclockwise as positive, you'd just be multiplying your entire equation by -1. So I have r times t minus r, because this would be the same distance there, same r, times t2. So I get then that r times t is equal to r times t2, which is 250. And when I cancel the r's out of that, I get that t is equal to 250 pounds. Okay, so t is equal to 250 pounds. Well, that's nice. Why didn't Cx and Cy come into here? Well, remember, I'm summing the moment about this center point here, and those forces intersect that. So that's why they don't play in here. They will in these equations. And again, had you taken counterclockwise as positive, you would have had a negative and a positive, and you'd come up with exactly the same equation and result. Well, let me sum the forces in the vertical direction, or maybe I'll say the y direction. I'll go ahead and take positive up. And here I have then Cy, that's going up, plus this piece of t over there, t times the sine of 30, minus 250, right? So I could say that's equal to 0. Sum of the force on the y is equal to 0. So Cy turns out to be equal to 250 minus t times the sine of 30. Well, t is 250. Making that substitution for t there, 250 times the sine of 30. So what's that turn out to be? 125 pounds. Let me double check that with the calculator. I think that's correct. Yeah. £125 pounds. Good. Okay. So that's Cy. If I then look at summing the forces in the x direction, and I'll take to the right as positive there, setting that equal to 0. What do I have? Well, I have minus Cx, because that's going to the left, plus the horizontal component of t, which is going to be t times the cosine of 30. This has no horizontal piece. I've taken care of that. That is purely vertical. So I think I am good there. So I could say then, looking at solving this equation, that Cx is equal to t times the cosine of 30. What's t? Well, that's where we put that 250 again. So I have 250 cosine 30, which should turn out to be 217 pounds. Is that right? Let me double check that. Yeah, 216 and some change, 217. Good, 217 pounds. So I came up with this Cx and Cy. If I was to design the pin here or the bearing that might be in there, these two numbers could be very important. If I was trying to figure out to design the cable or something, or the hoisting mechanism to pull this in, the value for t would be very important. A couple of things to note as I look at finishing up this problem. I actually did this in the order. If I had done this on my own, I probably would have done this one first, because I knew I'd have to get this value, and then done this one second, and then come up here. But sometimes when you're just starting out, you end up doing this, and you have to have the discipline to say, hey, I don't have enough information, so I need to go draw a Freebody diagram of something else. I mean, you don't want to guess, because these numbers could be plus or minus negative plus or minus infinity, right? So you'd have virtually no chance of guessing it right. So don't guess. When you get to something where you don't have enough information, don't guess. Go draw another Freebody diagram, draw another Freebody diagram, and then start to work your way back with the information that you found. Now, another thing you might wonder, well, how did you put this tension in this way? Or how did you put this Cx in there and the Cy there? Well, with some experience, you can start to look at the problem and see which way the forces would go, but it's not really a big deal, because if I put Cx in the other way, had I put Cx in that way, what would have happened? I would have come up with a negative sign here, indicating that the true direction was actually opposite that. So even if you assume it in what you consider the wrong direction, your negative sign will tell you which way it should go. Now, I'd usually try and avoid negative signs, so I like to make a quick inspection, see if I can get them in the right way. But once in a while, the negative signs come in, and that's fine. You don't want to spend 20 minutes trying to figure out what direction that goes. Put the value in and go. When we get into 3D problems, it's going to be kind of hard to figure out by inspection. We'll probably just out of habit always put them in the positive direction, let the negative signs fall where they may. So this is, again, a good problem for you to work on. You might want to take this thing here, draw that, see if you can find those answers on your own. Good practice problem. Well, let's move on to one more problem for the day. A little Jib Crane problem. These are kind of fun problems. So let's see, 3, this will be 4. So let's say I'm given a jib crane. So maybe we've got a wall here. You can find this in a lot of different shops or manufacturing facilities or something like that. And they attach to the wall this crane rail here. Maybe has a point they attach to the wall there. And then it has a guy back here to support it like that. Okay, and that might be a cable or a rod. And then we have this trolley that sits in here. We might have our hoist on it, and then it would pick up the load. Okay, you've seen this before. This goes up and down, and this slides in and out. Of course, then would probably rotate on this axis here, so you could have a work cell or something and move heavy things around so workers didn't hurt their backs and were able to move things. Very common arrangement. So what I would like to do is take this thing, and let's say that we are given that this is a 3, 4, 5 right triangle. Maybe we'll say that this is 7 feet, and maybe we will say, let me move that arrow out of the way here and put a dimension on there. We'll say that this is 3 feet. And we'll say that our load, take my animation arrows out of there, we'll say that our load is 1,000 pounds. Okay. So what we'd like to do is we'd like to find the tension in the cable. We'll say this is C, B, we'll say this is A. So we'd like to find tension in BC, and we'd like to find the reactions at A. Okay, the reactions at A. So we'd like to find these forces at this pin at A. We'd like to find the tension in that cable CB, or that rod CB. So the first thing on any problem, really any problem from here on out, is to draw a Freebody diagram. Okay. If you're doing a multiple choice test, you know you're probably not going to be graded on your Freebody diagram, but you're going to have a very hard time getting the problem right if you don't draw a Freebody diagram. So we'll put this beam here. At A we have a pin, don't we? So right there we've got a pin, and we know that pin could support a couple forces. Let's say that this is AY, and maybe this is AX. And then over here, I have this tension. This is a classic two-force member, isn't it? So, I mean, instead of saying that I have a horizontal and vertical force at B, I'm going to say that force is directed back along the axes of that member. Because if I put a BX and BY there, I'll all of a sudden have four unknowns and I have a problem. But since I know the direction of this, I can say that's acting along that. This side would be 5, and we have, we'll say that that is just T. We could say TBC if we wanted to, but we'll just say T. We shouldn't have any more in there. And then we've got the load here, 1,000 pounds. This is 7 feet. This is 3 feet. Now, some of you might say, well, are we including the weight of the beam itself? We might say that that's maybe negligible. Normally, we probably want to include that. We're just beginning with our work here, so we'll leave that out. They haven't told us what that is. We'll have plenty of time to add that to our models in the future. But if it was negligible, maybe it only weighed 50 pounds or 20 pounds or something in relationship to everything else, and we could probably fairly easily say it was negligible. Might be more, and maybe we should include it. Maybe it's 500 pounds, and we definitely should include it, and then it would just be another force in here. Well, let's see. Have we got everything? We've got the load. We've got the tension at B. We've got the pin at A. I think we're good to go on this thing. So we've got a proper free-body diagram. I'll say that I'm going to take X in the horizontal. I'm going to take Y in the vertical. And I should be able to take care of it. Well, let's see. What am I going to have? If I sum the moment about A, setting that equal to 0, and I'll go ahead and take clockwise as positive. What am I going to have? Well, AX and AY intersect that point, so they're not going to play in that equation, but I will have 1,000. That 1,000 acts through this horizontal distance of 7. That's going to be clockwise. And then I'm going to have to subtract off, this vertical portion of T. So if I come up here with this T like this, it's at 3, 4, 5. Doesn't it have a vertical piece and a horizontal piece? And what are those? This would be 3/5 of T, and this would be 4/5 of T, wouldn't it? And some people would be more comfortable. This is oftentimes done. That's why I'm kind of making a big deal about this. When you have a 3, 4, 5, or 5, 12, 13, some of those common triangles like that, or multiples thereof, you can do this. If you're more comfortable going through this and saying, well, I have a T over here, and I'm going to find this angle, which is going to be the arctangent of 3 over 4. What does that turn out to be? 36.9. So I could say that this side here would be T times the cosine of 36.9, and this side here would be T times the sine of 36.9. Okay, so I want to find this vertical piece, so I'm going to say I'm going to subtract off. This is a little aside here. I'm going to subtract off what? The vertical piece, which is 3/5 T, times the distance that acts through, which is the total distance here. So that's times 10, right? And someone else might say, well, I want to use the cosine of 36.9. Well, what is the cosine of 36.9? If I run through that, I get, what, 0.7997. I could say that this turns out to be equal to about 0.8. And what's 3/5? Let's see. Did I get that right? 3/5. Oh, yeah, I've got 3, 4. I got 3 there. Oh, I have messed this up, haven't I? Good thing I stuck with this. I'm right there. This would not be, this would be sine, this would be cosine, so I'm okay with that. That's 0.8. So I wanted to use this piece here for the vertical, didn't I? Sorry about that. This is the horizontal. This is the horizontal. This is the vertical. So I need to really be looking at that. What's the sine of 36.9? There's 0.6. Okay, so this 3/5 that gives me 0.6 is the same as the sine of 36.9. So my mistake there was I was looking at the horizontal when I really wanted to be looking at this vertical piece. So whether you use the sine of 36.9 or whether you use 3/5, you're going to get exactly the same thing. Of course, if you're lacking a calculator and trig tables, this is a lot nicer to do than that. So that's why we talked about that. Now, speaking of this horizontal piece, that force there, that's in this direction, isn't it? Why did I not include that? Well, because it intersected with A, didn't it? I mean, you could put that in there. You could put in the 4/5 of t times the distance of, I mean, you put it in there, plus 4/5 t times the distance of x through, which is 0. So since it's 0, the whole thing goes away. So I normally will not write that. So you go through the solution of t here. What do you have solving for this equation? You have t is equal to 1,000 times 7 divided by, this would go to the other side. You'd have 3 times 10, and multiply this thing by 5. One thousand 100 and 1,167. So I should probably just call this 1,170, but I'll leave it like that so you kind of see where the numbers came from. I've got one too many significant figures. We normally stick with 3 significant figures. So that's the tension there, 1,167. Hopefully that seems reasonable. It'll be greater than this because while this load is here towards the middle and should only be, this point B would be supporting a portion of this load, this is at an angle. You could imagine as this cable got lower and lower, if the cable were to get lower and lower, the force would get higher and higher, larger and larger. So let's then move on and sum the forces at A, looking, or some of the forces in the horizontal and vertical. So if I sum the forces in the x direction, setting that equal to 0, I've got ax minus, that's vertical, so I'm really just going to subtract off this 4/5 of t, right? And if you don't like the 4/5, you could use cosine 36.9. So ax then turns out to be 4/5 of 1167, and 933 pounds. Okay, so that's the force in the x direction. You might have again wondered, well, why did you take x to the right and y up? Well, I just guessed. I guessed correctly, and I was able to avoid a negative sign. Had you put it in this direction, you would have got a negative sign indicating that the true direction is the other way. And you don't want to change it because then that's going to change all of your math. You just leave the force in that direction, and the negative sign indicates that it's opposite of that. That's why the Freebody diagram is so important, because this answer does not mean much unless you can see where it is on that diagram. Well, let's finish up then. Some of the forces in the y direction, setting those equal to 0, what do we have? Here I took positive to the right. Here I'm going to take positive up. So I'm going to say that I have ay minus 1,000. So that's horizontal. I've taken that. That's negative because it's pointing down. And then this guy over here, we've dealt with that before. That would be positive. What do we have? 3/5 of t. So I can say then that ay is equal to 1,000 minus 3/5 of t, which was 1167. So what's that turn out to be? You could use 3/5 if you wanted to, or you could say 0.6 as sine of 36.9. Came up with 300, didn't we? Okay, so let me double check those answers. T is 1167. The AX value is 933, and the AY value is 300. So again, I did okay on my guesses on my direction because I came up positive, which hopefully makes sense. You need something to support this because this is going to be pulling it down. And as this guy is being pulled back this way, that's going to try and move this whole thing that direction, isn't it? So we'll need something to resist that. So it should make sense that AX is going to the right, and a fairly large number. Now, if we were going to design the pin and the bearing here, these two numbers would be very important. If we were designing this cable or rod, this number here would be important. We'll talk about how to use that in strengths and materials spring term. If we're concerned about maybe we have an existing wall and we don't want this thing to punch a hole through the wall, recognizing and knowing about that number becomes very important. So our design is going to be based on these. Well, speaking of design, is this an exhaustive study of this situation? Well, not really, because where's the largest load in terms of AY going to be? Well, that's when the load's right over here, right? So maybe we'd have to analyze that situation. And when's the largest load for the tension in this cable? Well, that's probably when the load's way out there, right? And the other thing, and codes will usually help you with this, what happens if the worker's a little excited and slams the load into there? Could there be a force that way? Absolutely. Okay, you could end up with a force in that direction. I've put a lot of forces here, so refer to the Freebody diagram. But I believe the current code says you have to take 1/10 of the load here, so that would be 100 pounds you'd have to put slamming into that end there. So we certainly have not done an exhaustive study of this. Let me take that out and that out, that out, so the notes will make hopefully a little better sense when you look at it. But those are other forces that we might have to think about looking at other cases or simultaneous with this one. You could imagine if the load comes out here, it's hanging at this end and slamming into the end at the same time. You might have to look at those simultaneously. So a good problem. We haven't done every aspect of it, but it gets you to thinking about that. So when we continue on next time, we'll do a problem that might be a little bit similar to this. Maybe I'll purposely do kind of a bad job of guessing my forces so that I can get some negative numbers. We can practice with that as we continue on talking about equilibrium and free body diagrams, a very important part of statics, and we're going to spend some more time on that. So take care till then, and thank you for watching.